In this video, we'll go over the answers to question 1 to 10 of the 2020 New South Wales HSC Chemistry Exam. Question 1 asks, what is the function of the magnetic field in a mass spectrometer? The available options are A, it detects the mass of the particles, B, it deflects the stream of charged particles, C, it excites electrons to higher energy levels, or D, it produces a stream of electrons that bombards the sample. So, for this question, if you remember the general function of each part of the mass spectrometer, then you will know that B is the answer here, because there's the magnetic field that deflects the charged particles and allows them to be identified by their mass. If we look at a diagram of the setup from Chemistry by Blackman et al., it is quite clear. The mass spectrometer measures the mass of a molecular sample. Sample is ionized to create a stream of charged particles which is deflected to separate particles of different mass and picked up at the collecting screen or detector at the end. Importantly, as we see, it is the magnet that does the deflecting, and therefore B is the answer. Moving on to the next question. Question 2 asks, which indicator in the table would be best for distinguishing between a face cleanser with pH 5.0 and a soap with pH 9.0? We're then given a table of indicators, associated color, and their pH ranges. The important point here is that the last column, pH range, tells us the transition region, when the color changes from the low pH color to the high pH color. So for example, bromophenol blue is yellow below 3.0 and blue above 4.6. Therefore, to differentiate face cleanser and soap, we just need pH 5.0 to be on one side and pH 9.0 to be on the other side of the pH range. In option A, they are both above pH 4.6. In option B, they are both above pH 4.4. In option C, 5.0 is below 6.4, while 9.0 is above 8.0. And in option D, both are below 9.4. Therefore, option C is the only one that met the criteria, with the two pH values being on either side of the range, and therefore giving two distinct colors to the face cleanser and the soap. This means option C, phenol red, is the answer. Moving to the next question. Question 3 asks, which of the following compounds is the most basic? This is followed by ethane, ethanol, ethylamine, and ethyl ethanoate as options A to D. If you're familiar with the properties of alkanes, alcohols, amines, and esters, which options A through D represent, then you will know that only amines are basic under standard conditions. Therefore, option C is the answer. However, to get a better understanding of how this comes about, we can investigate each molecule. Firstly, technically, the most organic compounds can act as bases or acids under the right conditions. By definition, bases accept protons, the Bronsted base definition, or donate electron pairs, the Lewis base definition. Looking at ethane, it has no free electrons, so therefore cannot act as a base under standard conditions. Ethanol has an OH group, and therefore two free electron pairs on the oxygen atom that could be donated. However, being very electronegative, the oxygen holds on to these electron pairs quite tightly, and it is therefore not very basic. Moving on to ethyl ethanoate, this molecule also contains oxygens and therefore has free electron pairs on the oxygen, but again, with their strong electronegativity, these will not be donated easily. Lastly, the ethylamine has a nitrogen atom in its structure, which contains a free electron pair. The nitrogen is less electronegative than oxygen, and is therefore more willing to donate electron pair to a proton, therefore meeting the definition of a base, both the Lewis and Bronsted definitions. These are the references used for question 3, mostly around verifying the properties of organic compounds and drawing out the structure of molecules. In question 4, we are asked, which pair of compounds would be difficult to distinguish using infrared spectroscopy? This is followed by 4 pairs of molecules for options A through D. The quick way to answer this question is to remember that infrared spectroscopy allows us to distinguish molecules based on their functional groups, and realize that all pairs in the options, except for option A, have different functional groups. In option A, we have 2 alkanes, butane and propane, which contain only CC and CH single bonds throughout. Therefore, option A is the answer. We can also answer this question by eliminating all other options. Using the infrared absorption data table from the back of the exam, we can look at each molecule one by one. Starting from option D, methylamine is an amine with NH bonds, so we expect to see a signal in the range of 3300 to 3500 reciprocal centimeters. For propanone, there is a double bonded oxygen in the ketone, therefore we'll see a signal between 1680 and 1750 reciprocal centimeters. Therefore, with 2 distinct signals, we can distinguish between these 2 molecules, and option D is eliminated. Looking at option C, we have propanol, which is an alcohol with an OH group that will have a broad peak in the 3230 to 3550 wave number range, while propanoic acid is an alkanoic acid that also has an OH group, but this time the peak will be very broad and appear between 2,500 and 3,000 reciprocal centimeters, below the alcohol's peak. Therefore, this also eliminates option C. Option B has ethane, an alkane with only CC bonds. So we should only see a signal in the range of 750 to 1100 reciprocal centimeters for that case. While 1-propanol is an alcohol, and we'll see a signal at 3230 to 3550 reciprocal centimeters. With these two distinct signals, again, this also eliminates option B. Obviously, this now only leaves option A. But just to be sure, butane is an alkane, so any signal will appear at 750 to 1100 reciprocal centimeters, and propane is also an alkane, so we'll get signals in the same range. Because these signals would overlap, infrared spectroscopy could not be used to distinguish between these two molecules, and option A is the answer. Moving on, question 5 states a 13C NMR spectrum is shown, and then asks which compound gives rise to this spectrum. The options given are chloroethane, 1-chloropropane, 1,2-dichloroethane, and 1,2-dichloropropane. The first thing to realize is that all the options are chlorinated alkanes and contain the same functional group, so we'll expect to see peaks in similar positions for all the molecules. However, we can use the fact that the spectrum shows two peaks, one at 19 parts per million and one at 37 parts per million, to conclude that the compound in question has two carbon environments. We can therefore draw out the structure for each and determine which one has two carbon environments. Looking at option A, chloroethane, we can draw out the structure and label the first carbon as number 1. We see it has a chlorine, 2 hydrogens and a CH3 group attached. The other carbon is different as it has 3 hydrogens and a CH2Cl group attached. Therefore, we can label this as carbon 2. This means chloroethane has two carbon environments as each carbon has different atoms or groups of atoms attached. Therefore, option A is the answer. Now, we know option A is the correct answer, but if you want to be 100% sure, you can also eliminate all the other options to see that A is indeed the answer. So, we know that the compound has to have two carbon environments. For option A, we've already identified the two carbon environments that it has. In option B, we can start again with labeling one of the carbons as number 1, and then determine the rest of the labels. For the next carbon, we have a carbon connected to 2 hydrogens, a CH3 group, and a CH2Cl group. This is different to carbon number 1, so we will label this as carbon number 2. Next, we have a carbon with 3 hydrogens and 1 CH2 group attached. This yet again is different, allowing us to label it as carbon number 3. This means we can eliminate this option as it has 3 carbon environments. Moving to 1,2-dichloroethane in option C, we can again label the first carbon as number 1 and see that it has 2 hydrogens, 1 chlorine, and a CH2Cl group attached. Moving across to the other carbon, we see it has 2 hydrogens, 1 chlorine, and a CH2Cl group attached. Exactly the same as the previous carbon. Therefore, we have to label this as number 1 as well. That means that in this case, we only have 1 carbon environment in this molecule. And option C is also wrong as it does not contain 2 carbon environments. Lastly, option D is 1,2-dichloropropane. We will label this carbon as number 1. It has 2 hydrogens, a chlorine, and a CHCl group attached, which itself is connected to CH3. The next carbon has a hydrogen, chlorine, and a CH3 group from one side, and a CH2Cl group from the other side. This is different from the first, so we will label it as carbon number 2. The last carbon has 3 hydrogens and a CHCl group attached, which itself is connected to CH2Cl. This is different yet again, and so we'll label this as carbon number 3. With 3 carbon environments, this means that option D is also not the answer, leaving option A as we had determined before. These are the references used for question 5, a reference to 13C spectroscopy, and drawing out the structures of molecules using view.org. Question 6 states, the structure of a compound is shown. This is followed by a chemical structure and the question, what is the preferred IUPAC name of this compound? We then have 4 options to choose from. The quickest way to do this question is to go about and label the structure to determine its name using IUPAC nomenclature, or naming rules. The first thing to do is remember that the functional group is assigned the lowest number possible. The structure shown is an alcohol, as we see from the OH group, so therefore we label this carbon as number 1. This means that the rest of the carbon chain is determined already as well. This eliminates options A and C, as these have the wrong number assigned to the functional group. Comparing options B and D, we can see that the naming only differs with respect to the ordering of the side groups, or substituents. We therefore ask, does the lower number come first, or is it alphabetical? According to IUPAC rules, the compound is named with side groups or substituents ordered alphabetically. Therefore, option B is incorrect, and option D is the answer. Moving on to question 7. Question 7 states, the structure of 4 isomers are shown, followed by 4 labeled structural formulas. The question then is, which statement is correct? Compounds 1 and 2 are chain isomers, compounds 1 and 4 are chain isomers, compounds 2 and 3 are functional group isomers, or compounds 2 and 4 are positional isomers. Firstly, we remind ourselves of what isomers are. An isomer has the same chemical formula, but different structural formula. In other words, compounds 1 to 4 here all have the same number of carbon, oxygen, and hydrogen atoms, but their arrangements are different. Therefore, these are all structural isomers. Looking at the options, we have to choose between chain isomers, functional group isomers, or positional isomers. Chain isomers differ based on how the main carbon chain branches. Functional group isomers differ on how arrangements of atoms can lead to different functional groups, and positional isomers differ based on where attached groups or substituents are placed on the main carbon chain. If we start with option A and compounds 1 and 2, we see they both have double bonds, but their functional groups are different. Therefore, 1 and 2 are functional isomers, and option A is incorrect. For option B, compounds 1 and 4 have very similar structures, except the position of the C double bonded O group is in a different place along the chain. Therefore, 1 and 4 are positional isomers, and option B is also incorrect. For option C, comparing compounds 2 and 3, we can see that the two molecules have completely different functional groups and are considered functional group isomers. Therefore, option C is the answer we are looking for. Although we have our answer, we can round this out and eliminate option D as well. Compounds 2 and 4, similar to 1 and 2, have very different functional groups, especially considering the double bond is between different atoms in the two options. This means compounds 2 and 4 are functional group isomers, and option D is eliminated. Question 8 states, a weak base is titrated with 1 molar aqueous HCl. The pH curve is shown. This is followed by a titration curve. The question then is, at which pH value would the solution be most effective as a buffer? This is followed by options A through D with 5, 7, 8, and 9. Firstly, we remember that a buffer solution is a solution that undergoes only small changes to its pH when an acid or base is added. In this example, a strong acid is being added to the solution. Looking at the plot, we can see that the weak base acid solution changes very minimally in pH, between 10 and 50 milliliters of acid having been added. This region is closest to pH 9, and therefore option D is the answer. The next question. Question 9 asks, which compound reacts readily with sodium hydrogen carbonate? Options A through D are then a series of organic compounds written in structural form. Firstly, we recognize that sodium hydrogen carbonate is a weak base. Then, we can just consider the functional group of each in order to determine if they will react with a weak base. If we make our way backwards, option D is an alcohol, or more specifically a long chain primary alcohol. Option C is a tertiary alcohol. Option B is a ketone, while option A is a carboxylic acid. With a weak base such as sodium hydrogen carbonate, an acid-base reaction is a reaction that will readily occur. Of all the options, the carboxylic acid in A is the strongest acid, and therefore A is the answer we are looking for in this case. For the last question in this video, question 10 states, equimolar solutions of sodium chloride aqueous, ammonium chloride, and sodium acetate, or sodium ethanoate, were prepared. The question is, in which of the following are these salt solutions listed from least to most acidic? Options A to D then have different orderings of the salt solutions. Firstly, equimolar in the question just means we have equal concentrations of each. We also realize that when they ask for an ordering of least to most acidic, this means in terms of decreasing pH, or starting from the most basic and ending at the most acidic. What we can do is identify the type of salt of each in the list. This therefore relies on you remembering these for any exam, but some observations may assist in this. Namely, the weaker the acid, the stronger its conjugate base. And similarly, the weaker the base, the stronger its conjugate acid. The inverse relationship holds as well. So, NaCl, or sodium chloride, is one we are familiar with in everyday life, and this is a neutral salt. It comes about as the reaction from a strong acid and a strong base. NH4Cl, or ammonium chloride, is acidic, with the ammonium ion the conjugate acid of the weak base ammonia. And lastly, NaCH3COO, or sodium ethanoate, is basic, the ethanoate ion being the conjugate base from the carboxylic acid, ethanoic acid. The order we want, therefore, is basic, neutral, and acidic. For the list that we are provided, it should therefore be sodium ethanoate, sodium chloride, and ammonium chloride. Out of the options provided, this means that option D is the answer. That ends this video. Thanks for watching and see you next time.